Hello, Michael.
Hello, good morning.
Good morning. Okay, let's get started. Just a moment. Everybody, can you see my screen?
Yes.
Yes.
Okay, so here is the final exam information. You will take the final exam on November 20. This means this Friday. So the exam time like 10:30 a.m. to 12:30 p.m. This is the university allotted time. But likewise, the midterm exams you can start at 8:30. So the exam will be available at 8:30, and then the last time to submit is 12:30 p.m.
That's
So
very generous of you. Thank you.
yeah, like because I did for the midterm exam, so same thing I will be doing for the final exam. And as you can see, total 5 questions will be asked, but it is like comprehensive. You have to look all the chapters. That's why you see I have mentioned, please look at all class lectures starting from 2 to 33. 33 means the last class. And then all numerical problems, homework, you look everything. The midterm exam questions, and then total 5 problems will be asked. And then as I mentioned, question pattern will be the same as the midterm exams. And then also, this is just the reminder, please don't forget to complete SATI. You know that every semester you do. So please do this time as well. So I'm going to, that upload, still I did not upload. I'm going to upload this slide in, class lecture. So everybody can see. The title is Final Class, Class 34. It will be the title. So does anybody have any questions, comment?
No.
Okay, great. Yeah, just to remember everybody, like November 20. This is the university suggested date. This date is not determined by me. Midterm exam dates were determined by me, but this is the university suggested date. And then even the time, but I am allowing 2 more hours. Okay, now let's get started. I think today the first presentation will be biomedical sensor or the breath monitored sensor by Ashley, Roberto, and Christopher. So please share your screen and go ahead. I have permitted you to share your screen, please.
Do you see this?
Yes, I can see. Ashley, I can see.
Okay. Great. So good morning, everyone. My name is Ashley Jones,
My name is Christopher McBride.
And I'm Roberto Martinez.
and we are presenting on the breath monitor sensor. So the objective for our project is to first explain to you what a breath monitor sensor is, specifically a monolithically integrated flexible flow sensor. And secondly, we'll explain the purpose of it. And next, we'll show you the schematic. And then finally, we'll explain to you how it works along with the simulation. A breath monitor sensor is found in many healthcare facilities, and they help provide the healthcare provider with information on the patient's breathing. These sensors are helpful in ways by aiding and improving patient care, by providing a visual representation of the patient's breathing vitals. Because there is a huge variety of breath monitor sensor types, we decided to go with a more innovative approach. And the flow sensor monitor is just that. It is a monolithically integrated flexible hot film flow sensor attached onto a flexible silicone case. This sensor is placed on the patient's upper lip, providing a non-invasive way to monitor their breathing vitals. It is composed of a hot film sensor, a conditioning circuit, Bluetooth, and a battery. All of these components work together to give a visual representation on a smartphone or computer monitor that has access to Bluetooth. So more about how this works. Here you can see the flow rate of exhalation and inhalation. The heat flow sensor mechanisms by the changes in flow pressure. It recognizes exhalation by its higher airflow and inhalation by its lower airflow. Any pressures outside of the set thresholds would be shown on the healthcare provider's monitor so that they may treat their patients properly.
Continue from the flow rate figure. Here's our sensor that captures and processes the breath. It is a monolithically hot film flow sensor, and it is composed of 5 resistors and fed through a low-powered amplifier. Now what we're looking at right here, RB and RA, these are our balancing resistors. These resistors are inserted into the circuit to compensate for different changes. They have properties of increasing in resistance as current flowing through it increases, and vice versa. It decreases as current decreases. Next, we have our hot film resistor, which is RH. The flow sensor utilizes the hot film resistor and acts as a both joule heater and temperature detector. The temperature of the hot film resistor decreases and makes the resistance changes, and thus provides the information of the flow rate that dominates the cooling rate. Next, we have a temperature compensating resistor, which is RE. And as temperature rises, the resistance of this bridge increases, and this leads to an increase in the proportion of supply voltage in the bridge and increases the bridge output voltage. And our RT is an adjust resistor for modulating the overheat ratio of 50%. All of these resistors are fed through a low power amplifier to amplify our voltage difference, which is sent to our Bluetooth module. And on the right side over here, in figure B, this is our monolithically integrated hot film flow sensor. Also, this is a physical representation of what our sensor looks like. Also, here's a block diagram of our sensor. As you can see, we have the hot film flow sensor which captures the breath and is fed to our conditioning circuit. And then that is transmitted to our Bluetooth module, which is projected on a smartphone or PC, whichever one you're using to project your results. And on the right here, here's a physical representation of our module being used. In traditional methods, the airflow sensors are usually embedded in a tube to monitor the respiratory flow blowing through it. And the respiratory flow is collected in pipeline by a nasal tube or nasal mask, which unavoidably hinders breathing. This packaging case of the monitor was molded by using polydimethylsiloxane, which is flexible and biocompatible. This allows for less restrictive and more accurate results. And the respiratory flow blown out from the nostrils over the strip is detected in real time by the hot film flow sensor attached on the strip. The tube-free configuration makes the respiration monitoring non-invasive and obstructed to the breath of the patient. And we chose this module specifically because one, is non-invasive and can still provide optimal results that we were looking for. And here we can see some breathing patterns and respiratory rates you will see from some patients. On the left, here's a normal breathing pattern and normal conditions such as sitting. It is a sinusoidal wave, and basically just showing a normal heart rate of 12 to 15 breaths per minute. And on the right, we have some breathing patterns that represent someone with respiratory conditions such as hypopnea and apnea. And as you can see, we have like a different rate of breathing in different patterns form.
So for our methodology, we basically searched online and found different types of breath monitor sensors and eventually ended up selecting the monolithically hot flow sensor monitor. We looked up some basic components they would require and were able to determine the ideal ones to use for each section. Then we constructed the circuit through PSpice and simulated it in different conditions, such as the normal rate at which a person breathes, as well as when a person is active. we also attempted to simulate when a person has a disorder such as apnea and hypopnea. So this is our schematic. As Chris described earlier, it's a conditioning circuit combined with a sensor that is amplified with a low-powered op-amp. It compiles the signal and sends it to the Bluetooth, which in turn transmits it to the phone or PC. So this is the output for the simulation of a person breathing under normal conditions. As you can see, it gives off around like 12 to 15 breaths a minute, and it peaks at 5 volts. Now, this is the output for the simulation of a person breathing under active conditions. So it gives off around 40 to 50 breaths per minute, and it peaks at 10 volts. So for our conclusion, though we were successfully able to simulate the other two conditions, we were not able to simulate the disorders. Some limitations to the sensor are dependent on the overall quality of the components for the sensor itself. For instance, a sensor with a higher accuracy while also being frequently and conveniently able to be conveniently maintained will be much more costly than a cheaper alternative that trades off the benefits for the price. Overall, it does require a low power operational amplifier. A very common one would be something like that LM321. It has a max current rating of 50 milliamps, which is much more than needed since we only need around 100 microamps or about 0.1 milliamps. The sensor overall must physically be placed on the patient's face under the nose, which could potentially cause slight discomfort, but it is non-invasive, so it will not interfere with the breathing, which is certainly desirable. And then these are our references.
Okay, thanks Chris and Roberto and Ashley for your nice presentation. So is there any questions and comments for this group? Ashley, you are from the biomedical, right? Yeah.
Yes, sir.
I think you already know about this topic, right?
I have not seen this specific type of sensor, so this was interesting to me for that reason.
Okay. Maybe someone wanted to say something.
Sorry?
Maybe before asking you, someone wanted to say something.
No, I just wanted to say good job.
Oh, okay. Thank you.
Thank you.
Okay, thanks. Is there any questions, comments for this group? If not, then thanks again. Thanks so much for your nice presentation.
Yeah, no problem.
Yeah, and then any of you just please upload on the Dropbox. Just any of you. I mean, you don't all three. You don't need just one per group.
Okay, I'll submit it.
Okay. Thanks. Okay, bye. Okay, so the next presentation is about hearing aid by Saival, Jeremy, and Kyla. Please go ahead.
All right, hi, I'm Jeremy Porter, and this is Shaival Modi and Kayla Price, and we are presenting a circuit based on the hearing aid. The purpose of a hearing aid is to increase the volume of some sound input to a level comfortable to the wearer of the device, and that can be adjusted for each individual.
The purpose of hearing aids is to take the sound that the natural ear would hear and amplify the sound to a comfortable level. That they cannot restore normal hearing if the ear cannot detect any sound. However, depending on the patient's level of impairment, that could determine how much the initial sound that enters the microphone will be amplified. Although there are many types of hearing aids devices, there are 4 major parts in every hearing aid. They all contain a microphone, an amplifier, a speaker, and a battery. The circuit that we simulated has a microphone for picking up the sounds and converting the sound waves to AC signals. The transistor cleans up the signal so that the amplifier can adjust the AC signal to the patient's needs, and the receiver takes that signal and outputs the sound to a comfortable level for the wearer.
So here's the circuit of the hearing aid that we simulated. As it can be noticed, there's a sine source on the left-hand side that represents an input from the condenser mic. A 24-volt DC source on the right-hand side is the output from an op-amp with a gain of 8 that amplifies the voltage from a 3-volt DC battery to 24-volt that is not shown in the picture. Capacitor C1, as shown in the picture, is used as a coupling capacitor to reduce excess noise and feedback. Resistors R3 and R4 are used in proportion to provide an ideal biasing voltage to the base terminal of the 2N2222 transistor. Resistors R2 and bypass capacitor C2 are used to ground the emitter terminal of the transistor. And additional capacitor C3 takes care of excess noise and feedback before it hits the op-amp. The transistor acts as an amplifier with the biasing components and values used in the circuit. The output from the transistor is an amplified signal that is 180 degrees out of phase, commonly known as phase reversal. That output is supplied to an inverting op-amp, which will reverse the 180 degrees phase reversal noticed in the output from the transistor. The output from the op-amp goes to the load resistance of the earphones that the patient or user will use to hear properly. And here's the simulation results of the hearing aid circuit. The green wave in the graph represents the output from the condenser mic after the coupling capacitor has removed the excess noise and feedback. And the red wave represents the amplified output signal after the op-amp has reversed the effects of 180 degrees phase reversal from the output signal of the transistor. To control the volume of the circuit, the gain of the circuit can also be controlled. In order to do so, feedback resistor above the inverting op-amp can be used. Additionally, the ratio of R8 and R7 in the circuit will aid in manipulating the gain or the volume of the output signal.
In conclusion, utilizing these components, we were able to create a hearing aid similar circuit that could take some initial input and increase the gain at various levels to generate a greater output that could be variable depending on the individual. And these are our references, and thank you for your time.
Okay, thanks Jeremy, Saibal, and Kyla for your nice presentation. Is there questions, comments from anybody for this group? So which simulation tool did you use? Is it MATLAB or PSpice or any other software?
It's PSpice.
Oh, PSpice, okay. So did you try MATLAB or you didn't?
We didn't, because we had problems with MATLAB, so we just moved on with PSpice.
Yeah, we had problems with MATLAB and OrCAD.
Oh, okay.
Yeah, we had problems across the board, to be honest.
Got it. Okay. Okay. Thanks once again. Thanks. So please upload on the Dropbox, just one. Yeah. Okay, so the next presentation is about insulin pump and by Rajik and Emma. Please go ahead.
All right. Okay, this is my insulin pump project. The objective of the project is to use my current knowledge of circuits to design and simulate an insulin pump, and doing so, I'll better understand the functionality of an insulin pump. Introduction is an insulin pump is used for those who have type 1 and type 2 diabetes. Well, by many people with type 2 diabetes, and they need to inject insulin in order to control their blood sugar levels. They'll either inject it with a needle, pen, or they'll use an insulin pump. An insulin pump is a machine that allows insulin to be delivered automatically or manually, depending on your blood glucose levels. Although too much insulin isn't good for you because too much of it will remove glucose from the bloodstream, which isn't a good thing. And this is a picture of an insulin pump. And this is the circuit diagram I used. The working principle, a 12-volt Battery powers the circuit because the pump in the design is rated for 12 volts. The 300 kilo ohm and the 100 kilo ohm resistor form a voltage divider. This will lower the 12 volt battery to around 3 volts, which you use to power the next part of the circuit. The sensor and the potentiometers form another voltage divider. The input to this voltage divider is 3 volts. The output is based on the resistance values of the sensor and the potentiometers. The output of the second voltage divider is connected directly to the gate of the MOSFET, and the source pin of the MOSFET is connected to ground. This means that the output of the voltage divider is equal to the gate voltage of the MOSFET, which is V out equals VGS. Therefore, the output of the voltage divider controls whether or not the MOSFET conducts current between its drain and the source pin. The pump is connected to the positive voltage supply and the MOSFET's drain pin, meaning when the MOSFET turns on, the current flows through the pump and causes it to pump liquid. When the MOSFET is off, no current can flow through the pump, so the pump will shut off. So finally, this design means that depending on the levels you set for your blood glucose levels, it will control whether the pump turns on or off. The methodology and control algorithm, a closed loop system. So step 1, the glucose level is read. Step 2, the continuous glucose sensor will sense this. Step 3, depending on the previous output and the settings you have for your blood sugar levels, a certain amount of insulin will get ready to be delivered. And step 4, insulin is delivered, and this will then be repeated, and you can see that explained in the chart on the right here. And then this is my simulation on OrCAD. I wasn't able to properly simulate it because OrCAD didn't have the right sensor that I needed for this design, so I couldn't get it to properly simulate. So I just placed the sensor that was in the OrCAD and built the rest of the circuit. In conclusion, I might have not been able to properly simulate my design because I couldn't get the proper sensor in OrCAD, but I was able to explain the working principle and methodology of my design. And these are my references.
Okay, thanks, Rajek, so for your presentation. Is there any questions, comments for Rajek?
Yeah, good job.
Thank you.
Yeah, thank you. Thank you. Anybody? Any other comments? Question? If no, thanks again, Rajek. Yeah, so and then please you upload your presentation on the Dropbox.
Okay, thank you.
Okay, thanks. Okay, so the next presentation is like wireless electric vehicle charging by Julian and Jachre. So please go ahead.
All right, you guys hear me?
Yes.
Yeah, you're good.
Yeah, all right, so we are doing wireless vehicle charging. My name is Julian Wong, and I'm partner with Zachary Walters. We'll be talking here in a minute. The objective of today's project, we're just going to understand the fundamental characteristics of wireless charging, pretty much the fundamentals behind magnetic induction charging. And we're going to design a test circuit and perform some simulations. We're going to use LT-Spice and P-Spice and consider its viability in the real world. So the actual idea of moving current through the air, it's been around since the late 1800s, but it was really dangerous and it was inefficient. You can kind of think of like Nikola Tesla and like lightning flying through the air. Over the next century, we've harnessed that power of inductive coupling, provide things like wireless charging toothbrushes. They use magnetic coupling inductive charging to charge the toothbrush, and here more recently, open sheet charging has been instituted in cell phones. So you just set your cell phone down and it starts charging like magic. But those designs right now, we're sitting at roughly an 80% grid battery efficiency, meaning when you plug that phone charger in and then you set your phone down to magnetically charge, it's roughly only getting 80 to 85% of the power that you are actually sending from the grid to the battery. So here recently, to understand what wireless charging is, we're going to talk about magnetically coupled induction circuits. So in this, let's see here we go. This circuit right here, on the left side, you have your primary windings. On your right side, you have your secondary. On the primary side, we're going to have a source. And once that source creates a voltage differential to the inductor, that is going to create electromotive force that's in turn to move electrons in the secondary inductor, which provides voltage and current and everything to the secondary windings. Underneath that image, we have your relationship of the primary voltage and secondary voltage, primary current, secondary current, and number of turns, and you can see the proportionality between each other. So here is a example. We ran this one through SPICE. This is just a simple linear transformer. The primary side is running at 240 volts, like a house line, and it is a step-down transformer going with a 2-to-1 turns ratio. Drop it down to 120 manageable volts to go towards a charger. Now, one thing I did not talk about that Zachary is going to talk about is distance between EP and ES plays a huge role in wireless charging. And here in the past decade, where that distance is growing further and further and further. For our design, we're discussing being able to park a car in a garage and charge it. In the future, we're going to also be talking about the cars being able to charge as they're driving, or multiple cars being able to be charged wirelessly from one wireless source. So here is one of our ideal transformers, and I'll give it up to Zach to take it from here.
So to start off with, I looked into how much power for the fast charging scenario with the current large model, which is the Tesla, which is about 250 kilowatts, which breaks down to, it's 250 kilowatts with the largest voltage that I could find coming out of utility power being about 480 volts, which means we were aiming for about 520.8 amps after rectification and filter. Did some of the math out because it does need to be a filtered high voltage, high current when it does reach the battery, but it does have to be AC when it moves through the transformer so that it can actually basically get converted into a magnetic flux and be transferred from coil A to coil B. You're going to need a magnetic flux current carrying conductor and relative motion between the two. So by collapsing and expanding the magnetic field, you create that relative motion. So, slide. So this is our working model, our final output of this model. And this is just a standard ideal transformer with no distance between them. And the reason we started out this way is the earlier models actually, earlier wireless charging models for cars and even with your phone and toothbrushes have to use a very, very small distance to try and minimize the amount of losses. So our initial design, we kind of prototyped our way to the best answer. Our initial design in theory would work by either lowering the vehicle or having some sort of charger that can lower and create the perfect lineup just to prove as a concept that this can work and doesn't require any person to operate the actual charging module and actually plug it in. So go ahead, slide. So, okay, that works. So here, Yuki, as I was saying, magnetic lines of flux and relative motion between the two, being the collapsing field, as you move them further away, there's fewer lines of magnetic flux contacting the secondary coil. So the fewer lines means there's less power transfer. And go ahead, slide. Oh, there we go. This is the equation I was looking for. This one was really fun. This is a dipole field formula. And what this basically states is that as distance increases, you're going to be losing power at an exponential rate to the third power there. And those fancy ends with the hats, those are just unit vectors perpendicular to coil axes, which is a really fancy way of saying offset. So if you've ever rubbed two quarters together, right, when the center lines aren't quite lined up, that's what that's referring to. And then the R hat is actually a unit vector pointing from center of coil 1 to coil 2. And that, again, using the quarter analogy, if you angle those quarters at different ways, it's going to represent that. And those both also contribute to your losses in your magnetic lines of flux. So for this, we actually assume, since this is going to be non-human interaction, and the expectation is to be having self-driving cars that can park themselves and line themselves up, that there would be any kind of offset would be negligible. And if obviously the car is at an angle, it's probably because the road or the parking surface is at an angle. So hopefully that should be the same magnitude there. And so it all simplifies down to just basically being divided by your distance cubed. And slide. Which is really, really bad. The units moving about 10% of the distance relative to the size of the coil, moving 10% of the distance relative to the size of the coil causes a drop about 25%. Moving 20% is a drop of 50. Your standard car is about 130 millimeters from the ground. So assuming a large coil of about 1 meter in diameter means you would have a breakdown that comes out to about 400 amps and 300 volts. And this does fit the basic charging. The low level charging power on a Tesla is 12 kilowatts. So we are able to achieve that. However, we have to start at a voltage that is applicable to the fast charge. And I mean, you can see there's a ton of losses there just by moving the car off the ground, and having a system that raises and lowers your car, raises and lowers your charger just isn't viable. There's too many working parts that could break down. It also leaves very little clearance, and if there's any kind of trash on the road or anything like that, you wouldn't be able to use that system. And also the dream of charging while driving is virtually impossible at that point. So go ahead, slide. So here we have the long range, which Julian will talk to you about, some new and upcoming technology that helps reduce those losses to a viable range.
So we know that the biggest constraint with wireless charging is they have to be smack dab right on top of each other. But there's this one company within the past decade, they're called Witricity. They've been really pioneering something called resonant magnetic induction. So in basic terms, what that does, it allows much bigger range because the induction coils are tuned to a specific frequency. And when these coils are tuned to generated in all directions, like you would see an electromagnetic flux normally expelled from an inductor. Now they're able to pinpoint control which direction that flux is moving. Earlier, I mentioned that wireless chargers run at roughly 80 to 87% efficiency from grid to battery. By using magnetic resonant tuning, Witricity has claimed they're reaching up to 95% efficiency, which is roughly the same as if you were to plug something in with a power cable. With, and your equipment has really nice components. You're getting roughly 95% from grid to battery. So they're shaping the magnetic flux and they're able to send it in specific directions. So now we're able to charge things from a distance of maybe a meter away. About 3 feet away, you're able to get power. You hold a light bulb up to it, you're getting power. That is being designed more and more. The distance is becoming bigger and bigger, but you see that's the the biggest hurdle is the math behind the distance, because you have to use such a big coil, and you have to tune so much of the frequency. So here are the results of the LT Spice that Zach made for the supercharger. Let's see here.
Like I said, our methodology was pretty much just kind of prototype, get something to work, and then expand upon it. So our first one is just going to be a standard transformer being passed over, passing power between it, and then over to a resistive load. And then here we got a little more complex and started adding filters and rectifiers to smooth it out so that it could deliver a constant DC to the battery. And then go ahead, and that is our final kind of design. In a perfect world, we couldn't quite simulate the new inductive technology, the resonant inductors, partially because this is so new. It's only about 2 or 3 years old, and also because when I tried to access the research paper, they wanted $100, so I couldn't quite shell that out. But it is a new and upcoming technology, and like we previously said, with enough of these, because of the distance and direction that you are able to go with it, you would be able to put these all down the highway and basically charge your car as you are driving it.
So yeah, he just hit on that. So this designs and developments are continually improving. You're going to see distances increasing exponentially, but it's not just limited to vehicles. I know we're talking about vehicles, but this same technology is going to be for buildings. You're going to have wireless power throughout homes, throughout buildings. So pretty soon, wireless is going to be just as efficient as plugging in straight to the wall with the cable. And right here is all the references we used. Thank you much.
Okay, thanks Julian and Jasari for your very nice presentation. It was very informative.
Thank you, sir.
You did a great job. Is there any questions, comments from anybody to this group?
Yeah, can you put this presentation on YouTube? I kind of liked it.
A presentation on YouTube. So you are telling to Julian Jasari, or you are telling me?
Oh no, just
there's not enough production value.
No, I liked it. It was pretty cool. I always mess around with magnetic induction and things like that all the time. I thought that was pretty cool.
Oh, okay, great. Yeah, I mean, this is a very hot topic. I mean, currently all over the world, especially like dynamic wireless charging. Like you are moving on your car and then you need to charge the car. So, and in the future, maybe in next 10, 15 years, you can see a lot of car charging station nearby the road. And then you don't need to stop. You will be running, you will be moving, and then your car will be being charged. So this is called dynamic wireless charging. So anyhow, so thanks again. And Julian or Jasari, any of you, please upload the presentation file on the Dropbox. Okay. Today the last presentation is automobile ignition by Jerick and Zafar. So please go ahead.
Okay, let me just try sharing this real quick. Then if I do this, can you see that?
Yes, I can see.
Okay, perfect. So Zarek, if you want to start.
All right. So this is the automobile ignition system in your car by me and Faizan.
Okay, so the objectives are to better understand the operation and theory behind the automobile ignition system and design and simulate a circuit representing the system. So Zarek, if you want to do this. Hello? Okay, so for introductions, the parts are battery and ignition switch, the ignition coil, contact breaker, and distributor and spark plugs. So as you can see here,
All right, let me flip to the next slide. Battery and ignition switch. So the battery is like a standard 12-volt car battery. In good conditions, it's 12.2 volts to 12.6. And the ignition switch is just like when you're turning your key in the ignition, and it flips the switch there that allows current to flow to the ignition coil.
Sorry, my mic wasn't working, but
Okay, I was wondering. All right, cool. So you can do this part.
The ignition coil consists of a primary winding and a secondary winding. Around 1 to 100 ratio windings. The primary winding takes in the 12-volt DC from the battery when the ignition switch is open or closed. And this transfers current to the contact breakers, and which is right here. The contact breakers take in the current through this orange line into ground, and this square in the middle is a cam, so it rotates, and it'll hit this knob right here to open the contact breaker. And when the contact breaker is open, the current flows through this capacitor right here. When that happens, the magnetic field in the ignition coil collapses and sends around 22,000 volts through the secondary winding and high voltage lining. This voltage goes to the distributor, which also consists of a rotating part that doesn't contact fully for these plates that go to the spark plug. This creates an air gap in between the rotating part and the plate, which sparks across the 22,000 volts to the spark plugs. The spark plug consists of a capacitor and a ground, which when the voltage is transferred from the distributor will spark in the engine and create a combustion, which will run your engine.
All right, so mechanical, electronic, and digital timing. So the system we just described was mechanically timed, and this is common in older models of the engine, but for more modern purposes, electronic and digital timing are more common. So electronic timing uses an armature, as you can see in that picture up at the top right. Instead of using the contact breaker to trigger the collapsing of the magnetic field in the ignition coil, it uses this armature. And so it has a sensor, and it just senses these cogs teeth, right? So as it passes, it'll sense it, and it'll trigger that collapsing magnetic field. So essentially, it's just, it controls there's like a computer that controls the speed of this cog, right? And that triggers how many times this will collapse. So in digital electronic systems, they're more common to use microcontrollers and ECUs, engine control units. So based off of the air to fuel ratio and the needs of the engine, it'll do the calculations to make sure that the distributor and spark plugs are firing off at the correct times. And even in some more modern models of this, each spark plug has its own ignition coil. So that's also a really common thing to see. So yeah. So here is the circuit diagram that we made. So the battery, 12-volt battery on the left here, it goes into the ignition coil, right? This is a step-up transformer, essentially. We used an ideal one with a K value of 1 just because it would be easier to simulate without losses than with losses. But in reality, there would be some loss here. So here is the contact breaker. So for the contact breaker, we couldn't really simulate like a moving part, right? So that would be a little difficult. So instead, we used a voltage activated switch. And it would switch on and off at different times based off the voltage source. The voltage source we use like a 5-volt pulse, right? So it has a delay of 0.01 milliseconds, and it pulses every 30 milliseconds, and it's on for 1 millisecond. So it'll just be, in our simulation, since it was 100 milliseconds, it'll be like 4 different, or it's 4 different pulses. So this will flip on and off 4 different times. And this is the capacitor inside of the contact breaker to avoid high heat generation when this is flipped open. And over here is the spark plug. So we did the voltage right here going into the spark plug. And so that's what we did for our simulation. Okay, so here is the simulation without the capacitor. So first we set the capacitors to 0 just to show that like these massive spikes in voltage are like what causes the spark to happen. Of course, the capacitors are there to reduce heat generation when the voltage or when the switch is open. So here at these little dips, you see, this is when the switch closes and then it suddenly opens and the high potential spikes and causes a spark. So yeah, that is the sparks. Here is with the capacitors. So the similar concept, just instead it's oscillation instead to better dissipate that high potential. So talking about that, those results, this on the right here is sort of like what the results should have looked like. Ignore the blue wave, that's the current. So yeah, so it's open at first, the switch closes or the contact breaker closes, and then the contact opens and you have that big spark. So this is without the capacitor and this is with the capacitor. The output voltage meets our requirement. It's supposed to be 12 kilovolts to 25 kilovolts, but it can go up to 45 kilovolts to cause a proper spark for the spark plug. The dips in voltage is when the contact breaker is closed, and when it opens, the EMF collapses and a high voltage flows through the secondary coil and to the distributor. And then that's distributed to the spark plugs. And then the capacitors are there to prevent high voltage current, or to provide the whole high voltage current safely, a safe place to dissipate so that it wouldn't cause too much heat. In conclusion, automobile ignitions consist of battery ignition coil, contact breaker, distributor, and spark plugs. The ignition coil steps up the voltage. The contact breaker creates short pulses of high voltage current. The distributor distributes these high voltage currents to the appropriate spark plug, which then ignites the fuel in the piston chamber. Older systems use mechanically timed systems, while a gradual shift towards electrical and digital timing allow for more accurate timings and less misfires. The circuit diagram and simulations were developed to reflect the concepts in this design and reaffirm how the automobile ignition circuit achieves its tasks. And here are the references.
Okay, thanks Derek and Faizan for your nice presentation. So for this case, which simulation tool did you use?
I used LTSpice.
Oh, okay.
Because I'm most familiar with it, so.
Okay. I mean, you can use any software, but this looks like nobody is using the MATLAB. Yeah. Okay. Yeah. Okay. So, is there any questions, comments for this group?
I literally went outside, popped the hood, and I learned something.
Okay, great. Yeah. Thanks. Any other questions, comments? Okay. If not, so thanks again, Faizan and Jerick. Please, any of you upload your presentation on the Dropbox. Okay, with that, I think we are done with the presentation. So it looks like everybody presented well. So let's give every presenter a big hand for their nice presentations.